This video is for lesson 12.2. It's about arcs and chords, and you don't need to add anything else to the tip chart today, this chapter 12 tip chart. The vocabulary that they use in this lesson is actually from lesson 10.6, where we talked about arcs and chords. Actually, that was from chapter 10, not just from 10.6. Anyway, so the vocabulary is really some background vocabulary from chapter 10. All right, so there are a whole bunch of theorems in this lesson, but the good news is they're all kind of similar, so that's better than learning a whole bunch of them where they're all saying lots of different things. So you need to know how this is kind of organized. This is our box of theorems, and all of these theorems start out with in a circle or incongruent circles. So I drew congruent circles, but I could just be talking about within one circle. And that little heading is in the front of all of these. So all 8 of these right here are underneath this little heading in a circle or incongruent circles. Now you'll notice I kind of grouped them, and that's because the groups are converses. Congruent central angles have congruent arcs have congruent central angles. Those are converses. Congruent central angles have congruent chords have congruent central angles. Those are converses. So you'll see that that's how they're grouped. Now, number 9 does not start out that way, and you'll see why when we get there. Okay, so let me just remind you what some of this stuff is. So in a central angle, that means it's an angle at the center. That's why it's called a central angle. We're going to learn about a different kind of angle in the next lesson called an inscribed angle, but this one's central. If you have, in one single circle, if you have congruent central angles, or in 2 congruent circles, so same size circle, if you have congruent central angles. So let's say that in these 2 congruent triangles, we have congruent central angles. Let's say it's 80 degrees and 80 degrees. Well, what the theorem says is that means we're going to have congruent arcs. We're going to have arcs with the same measure, which may seem a little obvious since arcs have the same measure as their central angles. Then they're going to be the same measure arc also. Okay, so if you were told that you have congruent angles, that means you can conclude the arcs are the same, and backwards, if you had congruent arcs, you can conclude the central angles are the same. So these are the same. All right, next one. In one circle or in 2 congruent circles, if you have congruent central angles, they are going to have congruent chords. So same kind of picture, congruent circles. Let's say we have congruent central angles. Let's say they're both 80. They don't have to be 80, but I'm just picking a measure. Well, this central angle's chord, which we haven't really talked about, but there's a chord connecting that point and that point. That chord is going to be congruent to this chord because the central angles are congruent. And we could do a proof of that pretty easy because these are both radii, which means they're congruent triangles by side angle side. So that's a proof of that. All right, so if you have congruent central angles, they're going to have congruent chords. If instead you were told that the chords were congruent, then you could conclude that the angles are congruent. So this is congruent to this. Okay, if you have congruent chords in one circle or in congruent circles, if you have chords that are congruent, then those chords have congruent arcs. Okay, so suppose we have a chord right here, and it's congruent to a chord right here. Now this would happen in one circle or in congruent circles. If you had congruent chords, that means the arc of that chord, which is right here, this arc of that chord is going to be the same measure as this arc of that chord. So if the chords are the same, let's say this is, I don't know, 1 inch, and this is 1 inch, then that means their chords are gonna be congruent. Like that, and vice versa. If you were given the arcs were congruent, then that would mean that the chords have to be congruent. Okay, I drew this one in just one circle. Okay, if you have two chords that are equidistant from the center, same distance away from the center, this one's going to be used quite a bit. So if you have two different chords, now remember this could be in two congruent circles also. If you have two chords and those chords are an equal distance away from the center. Okay, so let's say we draw a distance, I'm going to make that, let's say it's 1 centimeter. And at the end of it, I draw a chord. And then let's say I go a different direction, 1 centimeter. So suppose that's 1 centimeter. So see, those distances are equal from the center. 1 centimeter that way, 1 centimeter that way. And I draw a chord. Well, those chords have to be the same length. They're an equal distance away from the center. Now, this picture, if you were to draw that with a ruler, it might be off a little bit. My circle might be a little ovular, you know. I tried to make it perfectly circular, but that may be, if you measure these, they might be off a little bit, and it may be that I didn't measure this perfectly. Anyway, if this really is a circle, and these really are equal measures, then the chords would have to be the same length. So chords that are equidistant from the center are congruent. All right, and then in this one, it says if a diameter, or remember part of a diameter, we may just see the radius. If it's perpendicular to a chord, then it bisects the chord in its arc. Okay, so let's say we have our center right here, and let's draw a diameter just like this. If that diameter, or part of the diameter, so maybe we only see this part of it right here. If it's perpendicular to a chord, so here's a chord, and it's perpendicular, then what happens is that chord is bisected. So the chord is bisected, and the arc is bisected. Sorry, bisected. This arc is also bisected. So that is what is happening there. Okay, so those are all the theorems for this lesson. It's a lot, but these up in here are real similar to each other. These are the ones you're going to probably use the most in problems. All right, let's do some problems. Okay, example 1. They want us to find the length of AB. So this is our missing measure right here. Remember, if there's no symbol over the A and the B, it means the length of it. So we're looking for how long that is. And notice that this has a mark on it. That's the distance to the center. So chord AB is that distance right there from the center. And then there's another mark on this distance, which means those are the same. If this is 4, this is 4, right? So these two chords in the picture, AB and this chord right here that isn't named, those are equidistant from the center, which means they're the same length. So this chord is the same length as this chord. And I meant to mark a right angle right there. So write in a right angle for me. Okay, that is also part of a radius that's perpendicular to that chord, so that's why I meant that to be a right angle. So what that means is that chord is bisected. So this actually uses the last two rules that we wrote down on the other side. It uses these two. All right, so since that's perpendicular, because I should have had a right angle there, this is bisected, so that means this is 5. So that whole thing is 10, and since both of these chords are an equal distance away from that center point, they're equal to each other. So AB is 10. 10 units, we don't know what it's measured in. And so that's how to do that one. Question number 2. It says find the length of the radius. So again, I forgot to mark that right angle right there. So in the pictures in the book, there'll be a right angle right there. Okay, so we have a partial radius right here. See, we could extend that, and there's a diameter, or there's a radius, right? And it is perpendicular to that chord, which means the chord is bisected. So that 14 is cut in half because of that right angle, that's perpendicular. So 7 and 7. So we don't need the 14 anymore. Those are both 7. They want the length of this radius. Well, that's a right triangle. And to find the missing side of a right triangle, calling that R for radius, you can use the Pythagorean theorem. A squared plus B squared equals C squared. So 3 squared plus 7 squared equals radius squared. 9 plus 49 equals radius squared. That is 58. And then you square root, and you get R is the square root of 58. Okay, now, I didn't put any directions about how to write this answer, so it's possible in the directions they'll have you write it as a rounded decimal. So remember how to do a square root. You press second and square, and that gives you square root. You get about 7.6. If they want it as a simplified radical, that's where we did this whole breakdown thing where we did 2 into 58 goes 29 times. 29 is prime, so that means nothing comes out of there because there's not twins, there's not 2 of anything. So that means you would just leave it square root of 58. So the radius is square root of 58, or what did I say, 7.6? Square root 58. 7.6, or approximately 7.6 units. So it all depends on how they want the answer. If they say simplified radical, just leave it square root 58. If they want it rounded to 7.6. Okay, the last example, example 3. They want us to find out how long y is. Now, here's this should be a right angle again, so mark that. I just missed all my right angles on these notes. Sorry, guys. So this 15 right here is a radius. All right, here's the trick to this one, and this happens a lot in circle problems. Okay, so don't miss this. I want you to imagine that a radius is like it's on a spinner. You could take a radius and you could spin it and put it wherever you want in that circle. Okay, so imagine that radius right there could spin anywhere you want. Okay, well, there are some places it would be ridiculous to spin it because it just doesn't change anything. But if you were to take that radius and spin it to right here, I'll show you that. What it will do is close off this right triangle. It's still 15, so no matter where you spin that radius, it's still 15. And looking at this picture, my center looks so off. But anyway, so no matter where you spin that radius, it's going to stay 15. And so now I can work with this right triangle. So the big important idea in this problem is to think of a radius like it's on a spinner, and you could spin it wherever you want. And the most convenient place to spin it to would be to a place where you can close off a right triangle. Now, since that's a right angle, the chord is bisected. So instead of 22, I'm going to call that 11 and 11. Still 22, the chord's bisected. And now these are the numbers I'm going to use in the Pythagorean theorem. So Pythagorean theorem says this. I have 15 as my hypotenuse. So y squared plus 11 squared. Most common mistake is people leave that 22 and they put a 22 right here. But that would be crazy for one of the legs to be 22 and the hypotenuse to be 15. That's crazy. That can't happen. So y squared plus 121 equals 225. And subtract 121. Y squared is equal to 104. Square root. Y is the square root of 104. And then again, you look at the directions to see how they want this answer. So I'm going to see if 104 breaks down. 2 goes in there, 52. 2 goes in there, 26. 2 goes in there, 13. And then this one actually breaks down because we've got some twins right here. So these 2's bring out a 2. That 2 stays in, that 13 stays in. So it's 2 radical 26. Or if they want it rounded, it's going to be a little close to 10, right? Because it's square root of 104. Square root 104. 10.2. Or approximately 10.2. So it all depends on how they want that answer. Now remember, that's how long that is, so this would be in some kind of units. All right, so remember that a radius is like a spinner, and you can spin it to close off right triangles. That is all to that. Okay, thanks guys. Have a wonderful day. And I really am missing seeing you guys. It's starting to get kind of close to the end, and I miss you guys. So I hope you are having a great day.